Okay, thank you, Joe. So I will present here a work I did. Andrea Olivo was an M2 intern, and now he's a PhD student, so he did most of the work. But I'm the professor, so I did with Andrea. Well, you know, the reality is the opposite. It was a work we did just before I joined the team of Damien, so that's why you don't see Leipzig. So I was at Laboratoire Mécoton at that time, and it was done with help with the mint of the LUMAT Fédération. I mean, just they have a really big computer, which was useful for us. So the question is basically, we wanted to optimize optical Bell measurements. So what are Bell measurements? I don't know how many of you followed such quantum information courses, but a Bell measurement is a really basic tool used everywhere, from teleportation to quantum relays to, the quantum repeaters Eleni spoke about, to prototypes of photonic computers. So you have Bell measurements anywhere. And the main idea, it's a measurement on a set of 2 qubits. And typically when you prepare 2 qubits, the easy way to do, they are not entangled, but you can measure them. You can find a basis, an entanglement basis of the 2 qubits. So basically all those 4 states are distinct, orthogonal, so you can make, in theory, a measurement which distinguish them. And that tells you what would happen if the qubits were entangled. That would be in one of those 4 states, and that forces the entanglement. So it's a bit tricky technical stuff, which is a way somehow to untangle qubits which were not entangled, and it's used to propagate correlation, and that's why it's really useful for teleportation or whatever. So I will not stress here why they're useful, but the big problem is this measurement. It's really a theoretician invention. It's okay, it has a simple mathematical formula, but then the problem to do that, you already did very small, arguably the smallest, but a small quantum computer. Because you need to have a control not gate. So you need to have if you do it with photons, which is what I am interested in now, you need to have really, really, really powerful nonlinear optics. Mean that nonlinear optics is a kind of optics which was only possible with the advent of the laser. It's the only moment when we had enough power. But to do the kind of nonlinear optics to implement a CNOT gate, it should work at the level of already a single photon, so at the lowest possible energy. So in practice is, not totally undoable, but really hard to do. So then the question is how to do that. And so I will look at how to do that with linear optics, but imperfectly. But that means I will not be able to distinguish all the 4 states, but I will have what we call in the literature an unambiguous measurement. That is, I want a measurement which never makes any mistake, but which can fail. The easiest unambiguous measurement is a measurement which always answers, I don't know. You put the state, what state it is, I don't know. It's the easiest way to never make an error is to never answer. But you have ways to answer sometimes with a given probability, but still never make an error. So it's a bit harder than this trivial stuff. And of course, we want the maximum possible success probability. So the 2, I just told you before, I don't want it to be with nonlinear optics because it's really hard. I'm a theoretician, but I have experimentalist friends who want to do stuff. So, and the big advantage of linear optics is easier. It's basically an example. This is an example of a linear optic circuit. So you have, because I'm going too far and too close to, okay. So basically here the red lines represent the beams the photon follows, and then all those rectangles, white rectangles are basically engineered piece of glass. So you don't require any energy, and if everything is properly aligned, which for a theoretician means if every computation is easy to do, which for an experimentalist means, oh, I need an awful lot of work. But if everything is properly aligned, synchronized, all the photons are indistinguishable of everything, then you have some interference happening. And at the end, so the photon which are, I mean, here is the input, here is somehow output. The photons, where you find the photons here depends on the state you had at the input. And those semicircles represent photon counters. So when you have a photon, they click. When you don't, they don't click. Again, for ideal ones, and I only look at, but we have quite expensive but reasonable approximation of those photon counters in the lab. So that would be something easy, and I will look just at the static linear optic stuff, because you could also have something that when you have a click here, then you forward the electric signal to change the property of this piece of glass, which is even harder experimentally, and you have to do it very fast because the photons travels at the speed of light. So it's doable. You can do more things with that, but it's harder experimentally. Okay, hard experimentally is my excuse, because also it's simpler for the theoretician I am. Because any network of pieces of glass, beam splitters, and so on I have here can be described by a simple unitary matrix. So I have a really well-defined mathematical framework to look at all those interferometers. It's a unitary matrix, and then if you look at the second quantization framework, then basically the output creation operators are just a linear combination of the input following the matrix. I mean, either you have been told that and you know it already, or you don't care. And if you don't care, it's just, what I want you to know is just, if you do static linear optics, you have just a matrix which describes any kind of optical circuit, if you want, and we have a way to compute that. So that the tools, what I want is to do a Bell measurement. So what was known before the start of Andrea's internship? There is a setup which is known, actually it's a simpler version of that. The simplest stuff you can have is here is a 50-50 beam splitter here. And let's say forget about those, just one detector here and one detector here. And if you encode your bits into polarization, then just by symmetry consideration, if you have at the input the state psi minus, then you will have the two photons ending in two different beams. And for the three others, the two photons end up in both on one side or both on the other side through Hong-Hu-Mandel effect. So that's a small computation we usually do in the last lesson of Master 2 Quantum Optics, because it's a nice example. And this is known since I think since the 80s or 90s, and it's the tools basically used in the most, in most photonic experiments when you need a Bell measurement is this one, which works 1 times out of 4. We have 4 states, phi plus phi minus, psi plus psi minus, and it's just say, this detector just say, I have a psi minus or I have one of the 3 others. So I have a failure, but 1/4 of the case, it has psi minus and knows it, and there is no error if everything is ideal. So that's an example I'm going to use. The optimal, which is the one proposed by Braunstein and Mann in '95, was you add here a polarizing beam splitters, and if you look into more detail, so basically that notation means here I have 1 photon horizontally polarized on the left, 1 vertically on the left, 0 horizontally on the right, 0 vertically on the left. I mean, and those, so these 4 numbers correspond to the number of photons arriving in here, 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 here. And if you do all the computation with that, including the polarizing beam splitter, then you have that. If you here you have psi plus, you have that. If here you have minus, you have that. If you have phi plus or minus, you have these. So basically, you can say, okay, if I have two different clicks, then whether they're, I mean, for example, this term corresponds as this one clicks here or here, and it only comes from psi plus. And you can follow all them, and you can say, okay, I have either this one or this one. Oh. So I can distinguish those two, so half of the 4 case, and those 4, they're indistinguishable. I mean, there is just plus minus, which is a phase we don't measure, but you have 2 photons in one of the detectors. So it brings a 50% success probability, so it's well known, and in 2001, Calsamiglia and Lütkenhaus shown that there is no way you could do better with linear optics and no extra state. Actually, Calsamiglia and Lütkenhaus said both that there is no way you can do better if you don't inject extra light. And they also had 2 years before, I think, another paper where they said that if you inject extra light, you cannot do any perfect Bell measurement. But for most of people, that means basically everyone in the field but Calsamiglia and Lütkenhaus, and people who work with them, so including me, people mix the two results and say, okay, that's the best we can ever do. And so work on that almost stopped 18 years ago because people thought it was impossible. And often when I present that to photonics communities, say, oh, we know it's optimal and you can't improve that. And basically the initial idea of my internship with Andrea was, okay, that is optimal, we try to generalize that to other stuff. But then we did a more careful bibliography and we saw that actually Calsamiglia and Lütkenhaus didn't prove what we thought they proved. And there is a way to go beyond 50%. And there was a proposal in 11 by Grice with a probability 3/4. And the system is a bit complicated so that you have here, basically the red part is the same as before. So you enter your 2 photons here and here. And then you add an extra entangled pair and still on the blue line, and given the interference here and here, so you have the same stuff which will interact with the same kind of state, and given pretty long computations, so I recently put that as an exercise to students, and some got half of the computation roughly correct. So it's doable, but it's not trivial, because they're usually good students. And I didn't record how many I got the computation wrong. But then you can have by this analog, I mean, by computing all the interference terms, then you can find that you have 3/4 probability. The problem is that you need an extra entangled pair, which is absolutely identical to the first pair. And by symmetry, then, so that reduces the failure probability from 1/2 to 1/4. And if you want to divide it by 2, then Grice use the same symmetry at another level. So, I mean, their interferometers looks a bit like fractal. Each level contains the same as before and bigger. So you just need a GHZ-like state of 4 photons, and then in addition to that, and you duplicate all that stuff, plus extra GHZ state, and it gives you a probability of failure of 1/8. And if you want to go to failure probability of 1/16, then you need an extra 8 photon GHZ state, and so on. All those stuff are really nice. I mean, I guess, I don't know him, but Grice is like me, an theoretician. Doing a 4 photon GHZ state, it's maybe doable, but it's really not easy. Doing an 8 photon GHZ state, no one knows how to do them, and then you increase. So it's a kind of a nice theory to say we can go beyond 1/2, but we'd like something simpler. And that's what Fabian Ewert and Peter von Luck thought 3 years later, and they tried to look at single photons. That is, you don't even want an EPR state here, but you use separable single photons. And they found that basically you use almost the same scheme, but you have 2 single photons here with interact with the Hongwu model. So the stuff is a bit more complicated. Then they have a 3/4 probability. But then they couldn't use the next level of Grice. And with lots of work, they found that they could go up to 25/32 success probability, which is a strange number. We don't know why it's this number, but for him, it's a good hint that 3/4 is not kind of an ultimate limit for separable single photon, but that's it. So here, contrary to here, the efficiency is so limited, but the ancilla, so the auxiliary state is simple. I mean, simple is single photons. I mean, 4 single photons, which has to be indistinguishable. It seems easy for me, and then I started to discuss with Pascal Senla, who make the best single photon source ever, and it seems quite hard to do. So, but it's, I mean, that seems quite hard to do when you discuss with that with experimentalists, that is, they laugh immediately. Here they say, oh, it will be hard and so on. So that might be doable later. But another point is that those schemes are always be defined with, are really highly symmetric, and we have no way to prove their optimality. So my main question is, I mean, what the work we did is we're trying to find, to find kind of a limit of how high you can do with a given amount of resource, and we try to find new schemes which are better. So in terms of quantitative stuff, you can, all those setups, you can describe them on this graph. So here is a log, I mean, in base 2 of the failure probability, the lower the better. And here is the number of extra photon you use, also in log scale, except of 0, because when I asked Joe, okay, I will make a nice log plot, but I just like a infinitely large on one side board. Only infinity on one side, but it was not possible. So I have to skew a little to have a 0 here. But here you have, so basically here is a failure probability of 1/2, and it decreases, I mean, almost linear. I mean, that means it's exponential in both cases. So that's the Grice schemes. The more resource you have, the lower you can go. And here, and the yellow is the two, basically here and here you have the two protocol of Ewert. But then we don't know how to go lower than that. So that's the state of the art now in this curve. So first, how can we, so for this research of an upper bound of the probability of success or lower bound of the probability of failure, we have found 2 ways. An analytical bound, so I have a really nice, I think it's really nice, but I'm not objective. An analytical way to count, I mean, to bound the probability of success, but just for polarization preserving interferometers. So I have interferometers which have some symmetry. I'm not allowed to mix horizontal and vertical polarization. So it's a bit unfortunate because this limitation doesn't correspond to something reasonable experimentally. It's really easy to move the polarization from one stuff to the other, but it's all what I could find. The positive stuff is that all the previous interferometers which are here are polarization preserving. So at least it would tell us that if you want to go beyond this bound, you need to go out of polarization preserving stuff. And also, we tried a numerical step, or even I prefer, it's not totally numerical, but computer aided search for generic interferometers, I mean, only limited to small, just to find if they had, for small size, if we could do better than this bound. So for the analytical upper bound, basically, we restart. So we have here beta, here is not our 2 input photon, and here epsilon is our ancillary state. And U is my way to draw a linear optic interferometer. As I say, it's just a matrix. And we have, I mean, and the state, you can decompose it in terms of superposition, where each value, I mean, what really interesting for us is a lambda that is all the term with a given number of horizontally polarized photon. Because you have a fixed photon number is in epsilon. And now I'm a theoretician, I'm allowed to add physically undoable stuff. So here I make a huge QND measurement. So QND measurement is a quantum non-demolition measurement. It's a theoretician measurement which say you measure the photon, it projects you into the state, the result of your measurement, but it's still here. I mean, it's insanely hard to do. There have been some proof of principle demonstration with cold atoms in cavity and stuff like that. It's insanely hard to do, but in theory it's possible. It's not forbidden by the law of quantum mechanics. So I make a QND measurement of here the number of horizontally polarized photon. So basically I measure the lambda I was discussing before. It's surprising to make that. I mean, I'm a bit of a stupid theoretician because I could extract all this information to the real measurement I do later. So I add an insanely complex measurement which doesn't add me any information. So why I'm doing that is that because I have the restriction of this polarization preserving interferometer, they commute. So that is, it's exactly the same if I do the measurement here, and I'm allowed to add that because it doesn't change anything, or if I do the measurement here before the interferometer. So somehow here I know the number of horizontally polarized photons in this whole superposition, and I send through the interferometer, I have the same result. And okay, I say I'm in statically nonlinear optics, so I'm not allowed to change the interferometer depending on the result of the measurements. And then that stuff basically, if you go look carefully given a value, I'm not exactly measuring the value of lambda, but it's lambda plus the number of horizontally polarized photons here. And you can see that if here you have a psi plus, or here you have a psi minus, or here you have one of the two phis, then the states here, depending on the measurements, they're mapped into 3 orthogonal subspaces, which means that I will always find a way from the result here to know that I'm on psi plus, I'm on psi minus, and then the question is whether I can distinguish those two. So this transforms the problem of distinguishing 4 states to 2 which are always distinguished. I mean, those are the easy ones. And the probability I have to distinguish the 2 last. And then I have 2 non-orthogonal states I want to discriminate. And now I replace basically that linear, I want an upper bound. I want an ideal system. So I replace this system of a linear optical network plus a set of photodetectors by an ideal measurement. So highly complex stuff no experimentalist could ever dream to do, but which is allowed by the law of quantum physics. And we know that given the states lambda plus minus, which correspond to phi plus and phi minus, we can write them, and we know a bound of the probability of success is something well known, which depends on the scalar product of the 2 states. So then I just put that, I suppose basically that I have that measurement apparatus which does as good, and which, since it's the ideal, it's better than this one, which is equivalent to the one we have. So that allows me to compute an upper bound, which is given in a kind of a non-trivial, it's a formula which you can have from the expression of the actual state used as the ancilla. And so you can state, we did in our paper, check many various, all ancilla we could think and compute the bound. You can have a looser bound because from that you can deduce lower bound of the probability of failure depending on the number of photons. This is 1 over the number of photons, and then you have an even odd probability. That is, you take the number of photon k of the ancilla, you add 1. If it's even, you keep that. If it's odd, you take the next one to have the next even. So that's what that means. But then we see that the more photon we have, the better we have. So we have some kind of force. And you can look at now these bounds. In terms of photon numbers, you have it's the red line, and which is always, actually those corners, so that each time the dry scheme saturates the bounds. So you don't have access to somehow this part, but in the long term, if you have roughly, in terms of scaling, roughly, you could slightly optimize in this area, maybe, but the GRI schema are optimal. And if you look at you need to look into more details into, so the yellow, okay, it's hidden by the green, you should forget here, I should have removed that line. So those are the single photon bound, and it's much higher. But if you take into account that you have single photon, the photons are not entangled, you can refine the bound and get the purple line, and then the GRIS is not far here, it's optimal. This one is not optimal. So the 3/4 is optimal if you have separable single photons, but the 25/32, which is not surprising, is not optimal, given for polarization preserving interferometers. So that's it for the analytical bound. Now we move on to, so as I said, the analytical bound is a bit unsatisfactory because it is, I mean, we have this polarization preserving constraint, which is due to our proof technique. The fact that I could move the QND measurements is only linked to that. And it's not experimentally reasonable. So let's look at more numerically and look at our linear networks optimizers. And here, basically, okay, I don't know how much time I have. Okay, but I mean, actually it took us a lot of time because initially we did that exactly like textbook quantum optics, and it was highly inefficient. But the nice stuff, if you have a highly inefficient program, which still runs for the small size, then you can find the place where it fails, and you can optimize. But you need to optimize to do that properly. You need to optimize on the program itself, because I would never have guessed where we should have optimized. But sometimes you have day when the morning your intern tells you, oh, I compute that, and it takes you 20 minutes. Oh, quite bad. It's much better than last week. And then at the evening, okay, I've implemented the optimization we discussed, and it takes 12 seconds. So that's almost 2 orders of magnitude in a single day. And over the time of the internship of Andrea, we gained something like 4 or 5 orders of magnitude in computation time. But it's an exponentially difficult problem, so we still didn't go very far. So because the idea is that basically the input state in terms of photons, you can write it as a polynomial into creation operator. So for those who know second quantization, if you have 1 photon in mod 1, then you have it's like A1 dagger applied to the vacuum. If you have 3 photons in mod n, then it's n dagger to the cube divided by factorial 3, or root of factorial 3, root of factorial 3, or whatever. So you have a recipe to give you a polynomial, and the output this same way is output polynomial, and the unitary transformation, the big matrix I discussed about earlier, basically tell you that all the AIs dagger are a linear combination of the CJ. So you basically write a polynomial, make the transformation, develop the polynomial, and then you have the set of terms. So it's supposed to be easy. And then a detection event is a number of clicks. So basically here at the end you have 1. Then if you have a CJ square, it gives you a probability. You can compute from that the probability to have a 2-click in mod J, and so on. So you need to do that, but you need to do that analytically, I mean, to have all the coefficients of the polynomial. And then you want to maximize the probability of success from that. So what we do, we actually made the computer work for us also on the symbolic part. That is, for each, we describe the state. I mean, the step one, we did it by hand. So that's the easy part. The input state, which is here is one of the 4 Bell states we want to measure, and here's the ancilla. And you write the second quantization output polynomial. So it's a simple exercise, and that one is a really simple exercise. I mean, it's the first question of an exam, and I'm not a sadistic guy. It's the first question, so that's almost every student who followed could do it. It's not the last one where I'm not sure of the answer. And then you compute you ask the polynomial to compute the polynomial. Sorry, you ask the computer to compute the coefficient or the coefficient of the polynomial and to deduce the probability of detection. And that's straightforward but lengthy computations, as we write in papers, or exercise left to the reader. So that's the part where we cheat with students, because it's not difficult, but it's really long. So it's not difficult for a computer, or it doesn't seem difficult for a computer. And then from that polynomial, so after all the optimization, then we use a routine to transform this symbolic representation of a polynomial into a small C program, which is automatically done, which is then compiled, and which is given as a routine for a numerically optimizer where I need to choose a good figure of merit. Because another problem we have is that we are looking at unambiguous discrimination, so we allow no error. But that means that if you move a bit into the space of possible stuff, then you add an epsilon error, and then that means that it's a function. The function you want to optimize is really discontinuous, so it's bad for numerical optimization. So we need to find good heuristics, which also take us some time. And I won't go into the details. So for example, if I just take the basic, I want to distinguish, so I have four modes, 0 extra photon, and that is a way to encode the phi plus mode, that is 1 photon in each, okay, so there's 1 photon in mode 1 and 1 photon in mode 3, or with the plus phase, 1 photon in mode 2 and 1 photon in mode 4. So which correspond to odd number are horizontal, even are polarized. So it corresponds to HH2VV, probably, as the way Joe told you in lessons. So now I replace all the A's by, if I take here the coefficient of the matrix, each of the A is a linear combination of this setup. So I have this polynomial as a sum, which I have to develop. And then I have all this term in the probability to have all this stuff correspond to this product. If at input I had a minus here, my phi minus, then I would have various minus here, which would correspond to different outputs. So okay, that's not too hard. I won't go into the detail. It's just straightforward. And so why did I ask Andrea to do it by a computer, not by hand? I always said, okay, it's stuff I give as an exercise. He's a master to internship. And the example I gave you was quite good. I mean, if you look at the Grice scheme, the smallest, then the total number of functions you would have here to compute is not these small numbers, but it's 1,320. And I think it's illegal in France to give that to compute by hand to an intern. But okay, after one of the set of optimization, which are the one which allows you to get order of magnitude, is that if they look lots of the same and you have lots of symmetry, so you manage to reduce this number to 5. So that is, 5 becomes doable. But if you look at the next iteration of the Grice scheme with success probability 7.8, then the number of photons is almost 500,000. The symmetry, you reduce it to 22, but those 22, so there are polynomials. And how many terms do you have in those polynomials? In total, in the 22 independent function, you have 1.8 million terms in the polynomial. So you have, and that's the part that quantum optics professors don't tell you when they teach you second quantization, is that, okay, you just have, as I told you initially, you have linear combination, you compute the polynomial, and you look at the term you're interested in. It really explodes. You have a more than exponential explosion on the number of terms. And if you heard about boson sampling, it's linked to really hard problem in mathematics and in complexity theory. So we have good reasons to know that there is no shortcuts. I mean, there is shortcuts to reduce that, but it will always be an exponential scaling. So why do quantum optics professors think it's useful to teach second quantization anyway? One of the reasons that the second quantization for fermion is used a lot in solid-state physics, and it looks a lot like the same, but the difference in symmetry make that you have lots of shortcuts for fermions. And in some specific case, it's still the best way to compute those stuff. So, and we want to compute what we can. So what we did, our result is, we first, another recipe which is, I mean, at least in France, not often told in programming classes. If you want to make a program to simulate a physical system, first test it with known results. Because usually you will have bugs, and it will give you impossible stuff, and then it will help you hide the bugs. So we use just with the simplest kind of ancillary with no extra, so okay, I mistyped, with no extra photon, so vacuum, and it's what I told you. I mean, polarization preserving bound predicts success probability. Okay, no, there is one missing. So, sorry, the test I haven't here is if you put vacuum, then we know, as I said, we know since 2001 that it's impossible to go beyond 1/2. And it was a good way to test our program to if we had better. And we found, we tested in many configurations, and after the initial stage, we don't count because we had to correct some stuff. So we found again the known limit of 1/2, and we found the 1/2 protocol or several which were equivalent. So now we move for the simplest kind of ancilla, an extra single photon. There is no known scheme, and we really hoped to have something slightly better than 1/2, even if polarization preserving bound predicts 1/2. But it's the simplest, so we can really explore. Numerically, we are quite confident we can explore all that. But numerical search said nothing new. Still 1/2 with a single photon. So, okay. Then what is more photons? And then the nice surprise comes with 2 photons, so the smallest, because the polarization preserving bound was 5/8, so which is above 1/2. Nothing was known before us above 1/2. We find something which is optimal, but it's something which was basically obvious after the fact. So we called it the half Ewert-van Look scheme, which was the Ewert-van Look scheme with 4 photons was this one. And if you split it in 2, then you have that, I mean, if you look carefully. But we didn't think before seeing the result, but by seeing the result, we understood. And it was not published anywhere before. Then we could go further and have slides, but we didn't go much far. And then for 8 extra photons, where they had a 25/32, we couldn't go here because it was numerically too hard. So what does I mean by numerically too hard is that for this one, okay, it took ages of my laptop, I mean of Andreas' laptop, then we put it on my fixed computer, it didn't work. So we went to the LIMAT Federation and can we have access to your cluster? Yeah, of course. So we have several core, and after 3, the smallest were working, and after 3 days, it crashed. Oh, memory overflow, I mean, you have used all your memory. We only had 128 gigabytes of memory, and it was not enough. So we asked, and we had the authorization to have one node just for us, and with 256 gigabytes, and it works and gave us the result that nothing better than before after 10 days of computation of a cluster. So it's kind just of, okay, 6 extra photons plus the 2 initial, so it's in 8 photons, you already have this kind of stuff with a cluster. 8 photons might be doable to, with a real supercomputer with huge dimension, but it's really a lot of work for small stuff. So this is the nature of exponential complexity. But still, we had a new result. And important stuff, we didn't notice initially it was so important. We thought it was nice, is that we beat kind of 50%. It's kind of the simplest case, which seems realistic-ish, but which beats the 50% limit. And we didn't realize that it was not just an academic interest, because 5 over 8 is 62%. Not so much better than 50%. But for photonic quantum computers, basically they use massive Lebel measurements, and there is a percolation threshold of 50%. So basically, if you have something slightly lower than 50%, then you cannot have arbitrarily large cluster, and you have lots of scaling problem. And if you are slightly above, in theory, you could have something arbitrarily large. So it's certainly something which changes the scaling from polynomial to exponential or the other way around. So it appears to have lots of application, and we raise a lot of interest on that. So the schemes, how does it look like? It's here you have your state, and half of the state you just measure with single photon detectors. I mean, as usual, I mean, the standard scheme I show you is basically didn't have this part. So you distinguish the state, and phi plus and phi minus, then you don't distinguish them. But if the photon, if you put phi plus or phi minus, there is a Hongou-Mandel effect, and half of the time it goes on the left-hand side, half of the time it goes on the right-hand side. And when it goes here, then you make it interfere with 2 photons, basically with different polarization, and well-oriented, then Hongou-Mandel allows then to distinguish the plus or minus 5 half of the time, and then you compute is 5/8. And we call that half Evert-Van Look because Evert-Van Look scheme is the same, where this part would be duplicated here. So the most symmetric. And they also, when we told them, oh, we found that it's interesting, and Peter said, oh, we found it too. I published it, I discussed that in a conference, and it was roughly simultaneous, but it was not in the literature. So we were independently found. I mean, of course, Peter and Fabian were more clever than we are because they found it from considering their scheme. While we knew their scheme and we didn't think of cutting in two. Just we need a computer to have this kind of high power to find and say, oh, it works this way. But we found it independently. And so we then tried with entangled ancillas also to bite 3/4, and we didn't find something better. We still have, the dry schemes need GHZ states, which are incredibly hard to do. So we say, okay, but maybe we could have extra ancillas. So bell pairs, but nothing more entangled than the bell pair, but we could have many of them somehow. And numerically, we couldn't go really far. But in the polarization preserving bound, if you look at the computation, I told you it is something like 1/k. I mean, if you forget the odd, even stuff and the rounding. But if you look more carefully, if you say that if your states are not GHZ state, but just pair, then you have a scaling in 1/√k. So a worse scaling, but still goes to arbitrary close. And so we have progress. And so that's a purple line here, which also applies to single photons. And so our extra contribution is this. With one extra single photon, we could go a bit lower. And also we had a small, I mean, this difference here is really academic because I mean, I forgot the number. Maybe I have it, sorry. Here, yeah, I mean, generalizing the half Hilbert volume, we have a 49 over 64 or something like that. So we had also a small improvement here over the best known scheme, but it's really a small one. But we still don't have a kind of a scaling. We are after more than 12 photon. We don't know how to improve the probability, but we still have hope given our bound that we can go arbitrarily close to 0. So basically, what we have found is, again, an upper bound of for some kind of interferometers, which are polarization preserving and which are saturated by known schemes. And our hybrid numerical symbolical search confirms the optimality of some schemes. And we have one new interesting scheme. And another negative result, but which is a result anyway, is that we explored many kind of ancillaries from W state, GHZ state. I mean, you have a program, it fails to find what you want, then you throw at it everything what you have. I mean, it's a kind of, the computer doesn't complain too much. And all what we could compute were, we couldn't find anything better than the 3/4. So it's, as I say, it's a negative result. That is, it gives you way, I mean, it's numerical, so we don't have proof, but it gives us good reason to think that there is no way to do better. And another, okay, that was this slide was taken from another conference, but something which we're interested to know is now we have something, an automated second quantization simulator, which can go for a few modes and a few photons. And then we can use, it was harder to do than we thought, and also it answered it answers the question we had. Why didn't anyone look at optimize it? Because it was harder. So some maybe have tried, but and it's probably really useful for other kind of quantum optics proposals than just Bell measurement. Okay, and that's it.
Thank you very much, Fred, for that wonderful talk. So does anyone have any questions?
Optimize not in the meaning of mathematical optimization. When when you take small lambda,
yeah,
since entanglement is independent of lambda, so then you take the smallest value for large extension of polarization, the smallest value for lambda, then you do in the low lambda range minimization, like instead of doing the expression.
I don't get what is, I mean, do you call lambda my number of horizontally polarized photon?
Yes, expression for P failure.
Yeah?
Which has sigma over lambda. Just
yeah.
If you take only the low lambda values and you do minimalization.
Okay, so somehow you want me to, okay. So
instead of doing the whole range of lambdas, you take only small range.
Yeah, but I cannot select the small range of lambda.
But in the low lambda region.
No, because
here, yes. Instead of taking lambda 0 up to k.
No, but even in low lambda region, I mean, you still have a total photon number which is the same and is as hard, practically. I mean, this problem of computing the fact that I have, and it would be the contrary, some stuff where all photons are on the same side, but quickly in the interferometer they're spread, and you really have the exponential number of polynomial terms in these techniques. And if you look something which is surprising in the boson sampling literature, I mean, maybe not everyone is familiar here with boson sampling. The idea of boson sampling is something which was proposed by Scott Aronson a few years ago, is that if you have a linear interferometer, a set of single photons here and lots of vacuum state here, so really with a few photons, and then you measure the clicks here, the probability to have a click here is given by a function called the permanent, which is known to be hard to compute. And okay, it's a strong simulatability problem Rawat spoke about yesterday. I mean, it's an example of that. But it's really hard to compute, even if the regime where you have really a few photons, basically in the regime where you have many modes, but square root of, if you have m modes, square root of m photons, so in the few photon regime, it's still really, really hard to compute. So that would correspond, I think, to the low lambda. So even those few terms would be difficult. And on another hand, also, I want to have a high success probability. And if I eject most of the lambdas, because at the end, if I keep just the small lambdas, I will forget most of the lambdas. That means I will put each time my measurement here, which is basically here, give me a high lambda number, I will put that in failure because I don't know to what that corresponds. So I will add automatically a quite high failure rate. And this failure rate is, so it will be below what we already know. So it will stay in the regime where it will stay in the regime of bad measurement, at least for this, okay, anyway. At least for this application of an ambiguous malmeasurement.
The other way around, you take the high lambda and then you take fewer states for the photons.
Yeah, but it's the same on both. Really high lambda and really low lambda are mathematically equivalent. The big problem is middle lambda, where basically almost all the probability in most circuits due to a phenomenon like...
to squeeze in between.
Yeah, but we will...
That's better mathematical technique.
Okay, then I don't know mathematical techniques which would allow to do that. But what I really fear is that given the link with a permanent problem, and you might end up computing a permanent, and which will be hard, at least in the generic case.
Yeah.
Because mathematicians tried. Because we tried, I mean, in the various optimization, at some point, we thought of a better technique of computing the permanent instead of just putting the polynomial, and we didn't gain anything. We lost. So it might be possible to go to one side, but then we need a really good technique to squeeze, as you say, to reach the region. I think it might be interesting in some other setup than this one, in the sense that using the same software and optimizing in the way we can test, but for something else than unambiguous discrimination.
We are going to get back here.